Isn't there a white plug? A white computer plug? Hey, what's going on, folks? Let's get this party started. So I want to get started up on chapter. I want to get started up on chapter 3, polynomials 3 stuff. But until I get to that, some of you wanted to go over what the homework looked like for chapter 8. So why don't we take a look at that real quick? It should be a pretty easy homework. This book didn't cover exactly what I wanted it to cover as far as function, as far as domain goes, in the way that I wanted to cover. And I can re-go over with you the 2 rules that I really want you to remember. But let's see what's how to do this homework is for this one. Let's see. Questions. All right, so let's see. Okay, so this one is asking you, oh, I see. Choose everything that's in the domain of this one. So you guys were able to do this first problem, right? Is that what you guys were having trouble with? We're looking at homework 8.1. Yeah, no, I'm just kind of helping you guys out with some of these concepts. Oh, you haven't had a chance to take it. Well, you need to do multiple ones in there. All right, here, let's read the problem. Okay. Every day in Austin, Texas, the USGS records an official high temperature for the day. It is measured in an official site in the airport. Explain why the temperature for the T of the first, or explain why the temperature on the T of the first. Wait, that's not probably that. I'm asking you for part B. Which of the following is in the domain of T? So I chose. There's 3 answers really. 256, 10 over 2, and the square root of 81. Would you like to know why those are the... Yeah, exactly, Sophia. It's because the domain of this function is all the integers. They're the days of the year. And they only take 1 temperature a day, so... You know, in reading the context of this thing, it's like, say, at 12 o'clock noon every single day, they are taking the temperature. And they don't take the temperature at 1 o'clock or 12:01 or whatever, so you can only get integers. 256 is totally an integer in there. 10 over 2 is the same as 5, so that's an integer as well. And square root of 81, that's 9, so that's an integer as well. 372 is an integer, I grant you that. But 365 days in a year, so you wouldn't really write 372 days. You would just probably write, like, you know, the second year already. That's outside of the... Oh, well, actually, let's see. Let T correspond to January 1st in 2013, and T represents the number of days in the year 2013. So if you're talking about 372 days after the year, you know, January 1st, 2013, you're in 2014 already. And so this function no longer applies. That's how I would justify getting 372 out of there. Okay, Bradley and Jenna says, you don't like number 2. All right, well, let's talk about that one. Okay. Hot Shot Supplies is looking for to buy a shipment of pencils from Quick Fix, an office supply, whatever, wholesaler. Hot Shot Supplies has enough available room to storage in its facilities to store as many as 500,000 pencils. Each pencil is 5 cents, but of course, taxes and shipping are additional costs for Hot Shot needs to consider. Let C of P represent the cost that they must pay. You may ignore all additional costs. Find a number between 10,000 and 10,001 that is not in the domain of C. So let's see. Give your answer part A. Oh. The way, let's see, what did you write? The domain is the unit of pencils that you can have. Yeah, exactly. That's exactly right. Sophia's got it. All you need to do is put in a number that's in between 10,000 and 10,001. Because can I buy 10,000.5 pencils? Right? Like they'll send you like 10,000 pencils and a halfway sharpened pencil or something. I don't know. Yeah, no. Yeah. So you can't buy 10,000.9 pencils. That's outside of the domain. Apparently your domain is you can buy any number of pencils. I don't think that they have any setup as far as numbers that are allowed. But you can't buy fractions of pencils. So apparently I told the computer to give you the correct answer as long as it's any number between 10,000 and 10,001. So you could put 10,000.34178,654 and it would give you the correct answer. Okay, Gianna, what you're saying is the domain is C. So remember when we have C of P, it's almost like looking at f of x. So P is like the x, and the x is your domain, usually. So in essence, our domain is talking about the pencils. If I wanted to talk about the range, which is the cost that is associated with a certain number of pencils, then that's when I would talk about the range, and I would be talking about the cost, as you said. But when we're talking about the domain, in this context, it really means the pencils that we're talking about. All right, so Jenna and Emily, you asked me to go over 8.1. Did I sufficiently go over it for you? I don't want to give you all the answers, but I think that I think this is a good conversation for us to have. Are we good? All right. I'll tell you what. I'll do number 3. There's only 3 problems. Okay. Find the least positive integer that is not in the domain of C. The smallest positive integer that is not in the domain of C. Well, you're right. That is a little complicated. Oh, I know. Yeah. All right. Think about this. I was thinking about it. I was like, they could have 1 pencil. They could buy 1 pencil. That's totally fine, right? They could buy 2 and 3. None of those integers are a problem that I would see. Yeah, I know. So when you ask me what is the least positive integer that you can buy, I can't really think of one until I read the problem again and I read it carefully. There we go, Sophia. Because I mean, think about it. Their storage, the room that they have set up to hold all the pencils can only hold 500,000 pencils. So they can't go and buy 500,001 pencils. That's a positive integer. Right, because the room is only 500,000 pencil big. It can only store as many as 500,000 pencils. So 500,001 pencils is outside of our domain. That's literally not allowed in my domicile, or at least in the domicile of the room. 0 doesn't count because 0 is not considered a positive integer. 0 is its own integer. It's not a positive integer. It's not a negative integer. It's a 0. 0 is neither a positive or a negative. The question says in the domain of P. Okay, why does it say not in the domain of C instead of not in the domain of P? Okay, Lucas, that's a good question. I I suppose it's because when we talk about C, when we talk about C, we're referring to C of P. The function is C as a function of P. Does that make sense? So your function itself, when we're referring to C of P, and we're talking about the domain of C, which is a function of P, then what we're talking about is P. If we're talking about the range of C, then we're actually talking about C, which is like the Y value. Yes, the C is the Y value. But when we're talking about the domain of C, it's almost like if I were to talk about the domain of F, we would be talking about the X values. Because the domain is talking about the input things. What goes into this machine? I think the first day that I ever talked to you guys about functions was like week 1 of Algebra 2, and I talked to you about chicken katsu. You guys remember that story? And I told you that there's certain things that are allowed to come into the function. Namely, meat is allowed to come into the function. So the domain of chicken katsu is edible meat or edible food, I guess. I can't make katsu pen or katsu computer mouse. So if I say, what is the domain of katsu? What I'm talking about is I'm talking about the meats, not the katsu, the meats. I don't know if that story just helped you out or if it confused you more, but I don't know. Does that help you? I see what you guys are having some issues with, and it's the vocabulary. It's interpreting how it's written and all of that kind of stuff. All right, and that's kind of the point of this chapter. So I'm fine with talking about it. I guess I shouldn't have gone over all of the homework because I didn't realize there was only 3 problems in there. Why are there 13 points though? Doesn't make sense to me. Huh, whatever. All right. Why don't we talk about, you guys tricked me. You guys are like, Emily's like, I don't get number 1. And then somebody else like, and Bradley was like, I don't get number 2. And then Jen was like, I don't get number 3. Huh. I don't know why the first one's worth 10. I think I should have made them all even. Anyway. At least the easiest one was made worth 10 points. All right. Why don't I pull up polynomials 3, and let's get started up on that one. These polynomials, has it been really bad? Oh, actually, Bradley, I did talk to an anesthesiologist, and I'll have that conversation with you in chemistry. No, it was a good conversation. I even recorded it. So I'll send you the notes on that. All right. Polynomials 3. Let's take a look at this thing. Open this guy up. All right. So here's kind of a recap of all we've done on polynomials. All right. We're finding out that back in the old school day, we did ax squared plus bx plus c. And this is actually called a trinomial. Trinomial. Why is it called a trinomial? Well, how many terms does it have? It has 3 terms, hence a trinomial. Does that make sense? When we were working with lines, we were actually working with mx plus b. And that is actually called a binomial. And it's because there's 2 terms, bi being 2 and that kind of stuff. Back when you were babies, you worked with the number 5 or something like that. That's called a monomial. 1 number. Does that make sense? And this was back quarter 1. And then when we started quarter 2, I'm just kind of giving you a recap. When we started quarter 2, we had stuff like x to the 4th plus 3x cubed plus 4x squared plus 5x plus 7 or something like that. This, I suppose, would be called a pentanomial. But to be honest with you, after we get beyond trinomials, we stop saying exactly how many there are. We just say polynomial at that point. Polynomial meaning many, so it has many parts to it. Not just three terms, not just 2 terms, but many. Does that make sense to you? And then we've identified parts of the polynomial. I think that this was polynomial part 1. We've identified parts of the polynomial where if we had like -7, where the leading term is really the only one that's kind of important as far as what the overall shape looks like. I can immediately tell you what this graph looks like. Just by looking at knowing that this is x to the 4th, I know that it's going to look something like this, where it's got 3 bumps and it starts and ends in the same spot, in the same direction. But the -7 acts just like the a term in our old trinomial when we were doing quadratics, right? So that -7 will actually make it upside down. And the -7 actually stretches it a little bit more than usual, so maybe it might look a little bit more like that. Does that make sense to you? All right, so that was chapter 1. And we called this first term the leading term. The degree of your polynomial is the exponent in the leading term. And the leading term would be the one that has the highest power in it. The leading coefficient, that was the number in front of the leading term, and it's just the number. The coefficients were actually all of the numbers. So these are all coefficients down here. Actually, every number you see, except for the exponents, of course, those are your coefficients. We cool with that? And we've talked about in probably pretty great detail about what x cubed functions look like, and x squared, and x to the 4th power, and x to the 5th power, and so on and so forth. And I think chapter 2, Poly 2, we looked at the end behavior of these functions. We said, if this thing is x to the 4th power, I know that it ends and starts in the same direction. Whereas if it were x to the 5th power plus blah, 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 then I know that it's going to start and stop in the opposite direction. And so we didn't really care about what the middle looked like. We just cared about what the end parts look like. I'm just giving you a recap. We haven't started Poly 3 yet, but that was pretty much the gist of everything we did. Are you guys, is that all right? All right, cool. Let's take a look. So, let's see. I like this one. This one's kind of cute. Kimo sat down at his table to do his math homework, and his mom asked him to feed the baby. Unfortunately, for Kimo, poi was on the menu, and what a mess. So when you feed poi to a baby, the poi gets everywhere. And so he had all of his math homework, and the poi was all over the middle of his charts or whatever, all of his graphs. And so now what he has to do is he has to match the graph to the equation, but he can't see the middle of it. Well, this is all warm up, so let's do this one real quick. For this first function right here, -2x, x, and an x. If I were to FOIL out everything here, what would the power of the leading term be?
Third?
It would be to the 3rd power, exactly. It would be x cubed. All right. What would the leading coefficient be?
2.
It would be -2. All right. So I would suggest that because it's an x cubed function, it would look something like this. But since there's a -2 on there, it would look something like this. Would you agree? If I were to graph that on Desmos, then it would probably look something like that. I can't necessarily tell you what the middle one, if it were higher or lower like that. I can't tell you whether or not it would go up and down like that, but I can definitely tell you that the endpoints would go this way and this way. So my answer would be h of x. It would be the bottom left graph. Do you see how that works? Without even knowing what the middle looks like, I can actually already tell you what the graph is going to look like. All right, let's try the second one. 3x to the fourth power plus blah, 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 and I don't even care. X to the fourth power gives me a function that ends and starts in the same direction. The 3, that one is a parabola that opens up. It's actually technically not a parabola. Technically, the x to the fourth power will probably look something like this, but I know it will open up. So I would say it's the first one, the top left-hand corner. Do you see how this game works? All right, let's try this one. What is the degree of the polynomial that I have for this third one? X to the what power? X to the fourth power, very good. Because look, I could painfully x plus 3 to the cubed times x minus 1, and then I put a negative. I could painfully multiply everything out. I could make this to the third power, and then what I could do is I could FOIL in that x over here. But remember, the only really important term when it comes to doing these end behavior is the first leading term. And I know that the first leading term comes from everything in the first part multiplied out. So I have negative x times x times x times x. That's what my leading term is going to be. The negative comes from here, and then the x and the x and the x and the x. So my leading term will be negative x to the fourth power. And then there's going to be a whole bunch of other junk after that. I don't care what that is. So I know it's the x to the fourth power, and I know it's a negative. Which one would you choose? F of x, g of x, h of x, k of x. K of x, very good. Because it's going down, and it's an upside down parabola, and it's also starting and ending in the same direction. Cool. Let's see. Here's more of a warm-up. All right, here we go. So, what I want to do is I want to use our math skills now to actually graph things. And now we're getting into what we're going to be talking about for chapter 3. And this still isn't something completely, I don't know, crazy. It's not crazy to me yet. So I think it would be pretty easy for us to cover today. Let's look at this. F of x is equal to x minus 2 times x plus 1 times x plus 4. All right. What is the end behavior of this graph? Tell me all about it. What are your thoughts?
To the third power.
It's going to be to the third power. Okay. It's going to open upwards. That doesn't make any sense. That makes sense. All right. Lucas, opening upwards doesn't make any sense because a cubic function doesn't really open upwards. It opens, one side opens down and one side opens up. If it were a parabola or to the fourth power or to the sixth power or something like that, then you could talk about it opening upwards. That makes sense to me. All right, so the ends are going to be in opposite directions. I have a question for you. Is it going to be this or is it going to be this? You say the second one.
It's positive, yeah.
Because it is positive, that's true. So it's going to climb up. It's going to, as it goes further to the right, from left to right, it will go upwards. Lucas, is that what you mean by opening up? Is that what you meant in the first place? Okay, all right. Then I agree with you. The problem is I don't completely agree with your terminology because opening upwards implies to me that it's a parabola. But I see what you mean. You're saying that if I were a roller coaster, I would be riding uphill. Going from left to right on this roller coaster, it would be going uphill. I also know that this thing will generally look like this, right? Now I have a question for you. What are the zeros? Ah, there we go. Go back to your old parabola days and look at it. It's saying that this times this times this is in factored form. Granted that it's in factored form and it's a cubic function, but it still can apply to the same idea. If this times this times this is equal to 0, then I can set each individually equal to 0. So either x minus 2 equals 0, x plus 1 equals 0, x plus 4 equals 0. So my zeros are at -1, -4, and also +2. So I would venture to say that my parabola looks something like this and this. Before I draw my parabola, let me get one more piece of information. And it's not a parabola, of course, but in parabolas, the leading coefficient is still out front of the factored form. Why isn't the leading coefficient? Oh, okay. What Sophia is saying is, why isn't there a number out in front here? Is that what you're saying? Oh, okay. Here's my answer. There is totally allowed to be a number out in front there, and that acts just like the A as it usually is. However, the one that we're looking at particularly just so happens to be the number 1, +1. So we don't even write it. That's why it's not there. Not because it's not supposed to be there, but because we were so darn lazy to write it that we didn't even put it there in the first place. We cool with that? All right. There's one more piece of information that I can glean from this I can get from this before I even graph this. And the question is, what is my y-intercept? I'll tell you it right now. It's -8. Here, I'll do this carefully the first time, and then I'll say, hey, well, I can. All right, here, check this out. Let me multiply this out slowly for you. I'm going to FOIL the first two, so that would be x squared minus 2x plus. Oh no, sorry, x squared plus 1x minus 2x minus 2. I still got to multiply that by x plus 4. So this would be x squared minus x minus 2. Notice how the last term in here is really just, it comes from the, in the FOIL, it really just comes from the L part of the FOIL. Does that make sense to you? This term right here, this -2, really comes from the last times the last, the -2 times the 1. I'm going to venture to say that that happens the same thing over here when you multiply in this 4. We can do it slowly. We can go x cubed minus x squared minus 2x plus 4x squared minus 4x minus 8. And this -8 really just came from the -2 times 4. Everything else had an x in it, so I'm going to combine these like terms in the middle. But really, when I'm looking for the y-intercept, I only really care about the number that doesn't have an x on it. Why is that? Well, because when you're looking for the y-intercept, what do you set equal to 0? You set the x equal to 0. So everything that has an x in it, even if it's an x squared or an x cubed or an x to the 4th power, will die, no matter what the coefficient is in front of it. So therefore, my x-intercept is -8. And here's another thing that I think is interesting. I mean, because, see, here's what we're doing. At this point, I'm giving you guys the tools so you guys can look at a polynomial and graph it in your heads without even using a graphing calculator. Desmos is now obsolete, my friends. We can use Desmos to check our work, sure, but we are better than that. And I think that's awesome. All right, here's another question I have. Can the y-intercept in this graph be a positive number? Yes or no? I want somebody to answer. I got a no. I got a definitely a no. Does everyone agree with no? Okay. You're completely correct. It cannot be a positive number. Because think about it. If this graph has to cross here, and then it comes around and it has to cross here, and then it has to cross this way going upwards and this one going downwards, then it has to cross this y-axis somewhere in the negative part. It can't cross in the positive part over here unless it crossed the y-axis again, or the x-axis again. Do you see that? So there's no way that it could be positive. Unless, of course, it crossed the x-axis again. And in this case, since it's a cubic function, it definitely cannot cross the x-axis. So I would venture to say that this is generally my graph. I can't say that it looks exactly like that. The only parts that I'm missing at this point is how tall these spikes actually are. But I've got a lot of points on that graph to be able to kind of tell you that even though you might see slight fluctuations, if I were to graph this on Desmos, I guarantee you that I got the x-intercepts and the y-intercept. The only other piece of information that would help me graph this thing a little bit better is to figure out these middle portions right here. I don't want to call them vertexes because they're not really vertexes. Vertex is a word that applies to parabolas, where you have like a pointy part, even though it's a curve, right? These are more like, well, in calculus we call them local maximums or local minimums. They're the highest point that it goes in this vicinity. In its area, it's the hill or the valley. That's what we call those points. We cool with that? But isn't that cool? I can graph something without even really working on it. I mean, not working on it. I can graph it without even really using a calculator or using a table or using anything. I just take a look at these things and say, based off of these parameters, this is what the answer has to be. Let's take a look at another one, because these are actually kind of fun to me. Oh, wow. This thing's pretty intense. All right, let's do this one. Let's do c of x. That looks tough. C of x, x plus 4. Let's do e of x. That looks even harder. E of x. It's x, 2x plus 3, x minus 3, x minus 6. All right. Here's my question. What is the power? What is the degree of this polynomial? To the fourth power. I agree with you. So it's going to start and end in same direction. All right? Here's my next question. Is the leading coefficient, to be honest with you, I don't even care what the number is. I just want to know, is it positive or negative? It's positive. In fact, just for, just to see if we understand, what is it? It's positive what? is positive 2. I agree completely. All right. What about the y-intercept? What is the y-intercept? You say 54? No. It's not 54. Tell you what, that one's actually kind of a tough one. Maybe we should get back to that. What are the x-intercepts? That one I forgot to ask. That was actually supposed to be the second question I asked. What is the x-intercepts? Okay, well that one is definitely 3. There's also 6. There's also -3/2. Remember, you set everything equal to 0, and there's 4 things to set equal to 0. So one of them is 2x plus 3 equals 0. 2x equals -3, and therefore x is equal to -3/2. Does that make sense to you? All right, there's also one more, x equals 0. That's because the first number right there is, I set everything equal to 0. Here, if I put x equals 0 into here, or if I put x equals 0 into here, it doesn't matter what the rest of these are. That first term is 0. And so you're literally multiplying everything else by 0. It kills everything. All right. What is the y-intercept now? Now this is the part I forgot to ask, but I'm coming back to it. What is the y-intercept? -18. You multiplied 3 times -3 times -3. I see. Okay. Here's what my answer is. All right, I finally got a how come from somebody. Okay, here. In order to find the y-intercept, what do you always do? I set x equals 0. If I were to plug in x equals 0 into here, what would my y value be? You see, in the previous problems, when we set x equal to 0 into this crazy one right here, when we put x equals 0 over here, it killed all these first terms, and all we had to do was multiply all the last terms out altogether, right? But in this problem, we have that x that's factored out in front right there. And that makes your parabola, or it makes, not your parabola, but it makes your thing be 0. Because if you plug in x equals 0 into there, it kills the whole thing. So the answer is 0 for x-intercept. So if I were to graph this, I would say that at 0, it goes here. At it crosses at, I'm putting down the x-intercept. So the x-intercept is at 3, 4, 5, 6. So it's at 6 and 3 and -3/2, which is the same as -1/2. So it's right about here. I know that it's a happy parabola. So it's going to kind of go up and up like this. And it crosses there. And it also, so I would venture to say that the parabola looks kind of like that. Why don't we Desmos this sucker and see if that works? X times 2x plus 3. X, all right, here we go. Desmos.com. X times 2x plus 3 times x minus 3 times x minus 6. And I'm going to scroll up just a little bit more, a little bit more. This is not the graph I wanted it to look like. I'm going to change the y-axis a little bit. Let's go from negative 10 to positive 10. There we go. I'm going to zoom out just a little bit more. There we go. Hey, isn't that the graph I wrote down? Isn't that cool? You guys think that's cool or what? No, I don't think that's cool. Yeah, that's pretty cool. Come on, help me out here. Get excited. Or don't get excited. I don't care. But I'm just saying. And look, if I were to take this and I were to multiply it all out, you would see what that polynomial looks like. But we already wrote it down. There. Here's Wolfram alpha. Yeah, you're right. You're right. The last bump is really far down, and I didn't really get the bumps correct, to be honest with you. All right. All I did was I copied and pasted what I had in Desmos into there, and all of this thing is it will graph it out. Maybe Wolfram alpha might be better than Desmos, but it will also multiply it out for us. Look, there's the graph right there, and here's what it looks like if I were to expand it all out. That is, if I were to FOIL everything, it would look like this. The leading coefficient is 2. You have an x to the 4th power. Your last term, remember the y-intercept is the x term that doesn't have an x next to it, or it's the part of the polynomial that doesn't have an x in it. Every single term in this thing has an x in it, so the y-intercept is 0. Do you see that now? The roots are at negative 3/2, which is where the x-intercepts is. They also called the roots. Negative 3/2, 0, 3, and 6. Yeah, this is that's the equation for it. I mean, this is everything you need to know about it. But we already know everything we need to know because we're that smart. I just think it's so cool. There is some complications with this game, though. And let's continue on with this thing, because I think this is kind of fun. I don't know. You guys might not think it's fun. You guys might think, oh my goodness, this is so boring. I can't believe he thinks this is fun. I don't know. How do you guys feel about this? Is this like mad science to this, or? All right, okay. Just make it. I just want to see if you guys like it or not, or if. All right. It's a little hard, but cool. All right. What about this one? G of x is equal to x plus 2, x minus 2 squared. Now this one is a little bit different. Why I don't get why one of the zeros was 0 on the last one. Okay, all right. Sophia, I'm glad you call me on questions. Let me explain this to Sophia real quick. Okay. Sophia, when I asked you for the x-intercepts, how do you find the x-intercept? How many terms do you see here? I see 4 different things. Do you agree with that? Yes, 4 terms included. So when you find the x-intercept, you say, if this is equal to 0, then either this is equal to 0, this is equal to 0, this, or this. And then so you say either x is equal to 0, or 2x plus 3 equals 0, or x minus 3 equals 0, or x minus 6 equals 0. Well, this is where we got the x equals 3 from. This is where we got the x equals 6 from. Literally, it's saying x is equal to 0, and you don't even need to solve anything. It's just telling you, hey, by the way, x is equal to 0. And then this is where we got that weird one that said x is equal to negative 3/2. Okay. Oh, by the way, on Desmos, I forgot to check. Where did it cross? Oh, look, it crossed at negative 1.5, which is also known as negative 3/2. It also crossed at 3, and it crossed at 6, and 0 right here. All right. Let's do this now. Let's erase this. Select, delete, go to the pen, do the pen. All right, I'm going to do this one. This one's a little tougher. What kind of function is this? Is it a quadratic? Is it a cubic? It's a cube function. All right, cubic. What is the leading coefficient? Is it positive or negative? That's really all I want to know. I don't really care about, it's positive. Okay. What is the x-intercepts? -2 and 2. Okay. Okay. This is interesting. What is the y-intercept? +8, I totally agree with you. Does everyone see how +8 works for you guys? To get the y-intercept, you plug in x equals 0, so you have 2 times -2 squared, which is also known as +8. We cool? Let's draw out some of these things for us. We know this is the graph. We know that it's going to end down like this, and it's going to start down and it's going to end up. As Lucas would say, it opens upwards, but I'm not really a big fan of saying opens upwards. I know that it crosses at -2 and +2, and I also know that it crosses here at +8. What does my graph look like? How can I have a cubic function that only has 2 roots? You see what I mean? Like usually my cubic functions look like this. But I don't have a third root to cross. I can't cross that x-axis at that point because it's not telling me I can. It's not telling me I'm allowed to. I'm just wondering what your thoughts were on that. Ah, there we go. What Lucas is suggesting is he's saying it comes up here, and then over here it actually it doesn't really cross. It just kind of, as he said, bites back. It's kind of like asking, when does a parabola, how can my parabola only cross at one point? Like when we were doing parabolas? Well, when it crosses and then it just kind of touches, it kisses the axis. It doesn't actually cross, it just kind of kisses it. So your x-intercepts, I didn't ever say that your x-intercepts were the place where the graph crosses it, the x-axis. I would always say your x-intercepts are the ones where it touches the x-axis. Now touching could mean just touching and backing off, or touching could mean touching and going through. So, and here's the interesting thing. What in here would give you a clue as to why this thing bounces back?
There's 2.
Because of the square. Yeah, I would agree. I would definitely agree. Do you guys see that? Let's Desmos that and see if our graph is, or Wolfram Alpha. I don't really care what we do with it, but we'll Wolfram Alpha and see if the graph we get is anything close to what they have. Let's see. X plus 2, x minus 2 squared. Ah, there we go. Crosses at -2. The y-intercept is at +8. And then it hits here at 2, and then it bounces backwards. You guys agree with that? You see it? All right, there's one more I want to do, and then we can move on to the next part. But I think this is kind of fun. I'm having a good time. I don't know about you. Actually, from what I understand, teaching isn't about me. It's about you. So how are you feeling? That's really my question. Or you feel like you're learning something new, or you're... All right, okay. X plus 5 times x minus 3 cubed. Okay. Let's see. How would we... Let's do this together. What's the degree of my function here? Fourth power. What you were going to say? What? You were going to say fourth power? Okay, fourth power. What is my? That says fourth power, not four hopper or something. I don't know. Fourth power. Sorry, poor writing. What is my leading coefficient? Positive or negative?
Positive.
Positive. Very good. What is my y-intercept? Well, it would be 5 times -3, which is -15, times -3, which is -45, times -3 again. What is -45 times... Or no. What is positive 45 times -3? That would be... why can't I think? I think it's 135. It would be... Sorry. I don't know why I'm not doing math in my head right now. It'd be 5 times -3 cubed. Negative 135. There we go. Okay. See, I told you it was 135. All right, my y-intercept is negative 135. All right, what are my x-intercepts?
-5.
-5 and
3.
+3. Okay. 1, 2, 3, 4, 5. 1, 2, 3. Here. I have a fourth power function, and I know that the y-intercept crosses way the heck down there at negative 135. Yes, Cameron, actually the equation would exactly be that. I think maybe that might be easier for you to see. It's fine. Okay, what's going on? Let's see. I know that it has to begin this way and end this way. Got it? I also know that it crosses here and then it comes down here. What happens over here, though? That's what I'm wondering. Like, my fourth power function usually goes like this, right? I'm thinking that it can do a few things. I'm thinking that what's going to happen... Sophia is saying, So what Sophia is saying is, when this was to the second power, what happens is it touches that spot right there, and then it bounces back, like a parabola would, right? But now what Sophia is saying is, since it's to the third power, maybe what it will do is, at that spot, it will kind of go right through. Which almost, if you zoom in right here, that almost looks like a cubic function right there. Locally. I mean locally as in like in that small vicinity. You guys agree? And then come up. I'll tell you what. There is no real justification for my answer. Why don't we just use the Wolfram Alpha and see if that actually is the case? It was x plus 5, x minus 3 cubed. So at these exponents, this like to the third power, it does something funky, and look what it does right there. So it definitely crosses here at -5. I agree with that completely. At +3, what ended up happening was, yes, it did go through, but it almost kind of went through like it was a cubic function in that small area right there. You can't see. Let me zoom in. Okay, can you guys see that a little bit better? Maybe if I graph it on Desmos, it might be a little bit more fun for you. Control A. No, oops, what did I do? Delete that. Parentheses. X plus 3. X plus 3. X plus 3. No, X plus 5. I'm having a terrible day typing. X minus 3 cubed. Caret cubed. There we go. So see, it goes through right there, right? And then in this area, it kind of comes up like this. And then it, if I were to zoom in right here and only show you that graph right there, you would say, oh, that's a cubic function, right? And I told you that, see how that thing is cubed right there, this part right here is cubed. In that vicinity, it almost looks like it acts like a cubic function. Do you see that? Anyway, what's your thoughts? Pretty cool? Not cool? I don't care. All right, let's try this one. This one looks horrible. I don't think it would be that bad. I mean, it looks horrible. All right, let's try this one. X plus 2 squared. X minus 1 cubed. X minus 3. All right. What is the degree, my friend? The degree is to the 6th power. I agree. Is it a positive leading term or a negative? It's positive. Okay, good. What is the x-intercepts? -2, 1, and 3. And you know what I'm going to do is I'm going to put a little 2 right here and a 3 right here. Or maybe I'll put M2 and an M3. The M2 stands for multiplicity. So it's of multiplicity 2. And what I mean by that is my x-intercept, if I were to write it out, like expand it all out, it would be x plus 2, x plus 2, x minus 1, x minus 1, x minus 1, x minus 3. And so if I were to ask you what is the x-intercepts of that, you would tell me, oh, it's -2, 1, 1, 1, and 3. Right?
Wait, what is that?
Yeah. This M stands for multiplicity, and basically what I'm saying is it's -2 twice of 2 multiples. And it's +1 of 3 multiples. That's kind of what I mean by that. Does that make sense to you? I don't even know, to be honest with you, if this is the way official mathematicians write it, but this is the way I wrote it when I was a kid. Is I said, is not only did I say here's the x-intercepts, but I also added the additional information that this -2 is special, and this +1 is even more special. And that 3 is just your average everyday x-intercept, so it probably means it just crosses right on through. Okay? Let's graph this. Let's graph this without even figuring out what the y-intercept is. I know that they asked of it, but, you know. All right. I know that this thing's going to start up and up. I know it's going to cross at -2, and 1, and 3. Here, here, and here. I would venture to say that at this point right here, it will go up in the air, like that. Yeah? It's going to hit that -2, but it's going to bounce off of it. Why is that?
It's 2.
Because of that multiplicity 2 right there. That's what the giveaway is for me. For this 3 over here, I would venture to say that's going to come back down, and it's going to kind of look like that. Or not for the 3, for the 1 right there. Because this one is raised to a cube power. And then for the 3, it's just going to cross right on through. All right. How many bumps does this parabola, or not parabola, but polynomial have?
6.
It's got 5. Do you see 5? See if we can identify them. There's one here, one here, one right there. How many, what I'm saying is, how many bumps are there? And I would almost say there's 2 here. It's kind of like, when I'm looking at a cubic function can have 2 bumps, right? But when I'm looking at exactly x cubed, I only see this. Well, it's because these 2 bumps are so close together when I have y equals x cubed that they almost overlap at that one spot right there, making it 2 bumps, even though it only looks like there's 1 bump there. And a bump isn't even the right word for it. But, see, here's the thing, is I'm all about having you guys take ownership of your mathematics. It's you guys who need to figure out how to do this stuff. So what I'm all about is, let's make up our own terminology. If there's no other terminology already out there that's being used, let's make up our own. I don't mind. And as long as you understand what it is. Of course, if there's official terminology that we would use, I would tell you that one. But right now, we're calling them bumps. How many times does this graph turn or get bumped back? And it gets bumped back 5 times. 1, 2, 3, 4, 5. I see it 5 times. Do you guys see that? All right, let's see. Oh, wow. Consider, what does this problem say? Oh, I see. They want you to sketch the graphs. Okay, all right. Hey, let's go on with our terminology, just looking up a little bit more. I actually don't think I'm going to give you this as homework. You guys can just skip this whole part right here. I'm going to skip this. We're going to look at this terminology. Polynomial functions can behave differently at zeros depending on whether or not the root is repeated. Hey, this is actually the explanation of what we're covering. So, polynomials can behave differently depending on at the zeros depending on how many times this thing is being repeated. They can do this. They can cross right on through. And that's when it's not a repeated polynomial or a repeated 0. It doesn't have a multiplicity in my 0 or my x-intercept. It could have a bump on it. And that would be like if I had a square or a 4th power or a cube function, or not a cube, but a 6th power or whatever. Or it could kind of look like a cubic function, and that would be anytime my root is repeated in an odd exponent. Does that make sense to you? Okay. To be honest with you, I covered all of chapter 3. And I think that's due in like the 19th or something like that. So it's due next week. End class early, sure thing. I don't mind. I will end class. You can leave. I'll see you guys back here at 2:15, I believe it is, for chemistry. Here's my question: is For those of you who want to stay, so I'm going to end class. I'm going to stop the archive, whatever. I'll do that right now.